Welcome. In this video, we're going to explore the concept of a process control block, also known as PCB. A process control block is the data structure for process management in operating systems. It's a crucial element that enables operating systems to effectively manage and control processes. Let's dive in and understand what it's all about. So, what exactly is a process control block? A process control block, or PCB, is a data structure maintained by the operating system for every process. Consider it as a container that holds all the essential information needed to manage a process. This information includes the process's current state, its unique identification number, priority, memory location, and a lot more. It is also known as task control block. PCB is created when a process is created. PCBs are stored in kernel memory space and get updated during process lifecycle. Each process has its own PCB, allowing the operating system to keep track of every process running on the system. Now, let's explore the primary purposes of a process control block. First is the process management. PCBs enable the operating system to track the state of each process and manage transitions between states. For example, from ready to running or blocked. Second is context switching. PCBs store all the necessary information to save and restore process context when the central processing unit, or CPU, switches between processes, ensuring smooth multitasking. Third is process identification. PCBs provide unique identifiers and attributes that help the operating system distinguish between different processes, preventing confusion and conflicts. Fourth is resource management. PCBs track the resources allocated to each process, such as memory, files, and input or output devices, preventing conflicts and enabling proper resource allocation. Let's delve into the key components of a process control block. First is the process identification. This includes the process ID, parent process ID, user ID, and group ID. These identifiers help the operating system uniquely identify and track each process. Second is the process state. This indicates the current state of the process, such as new, ready, running, waiting, or terminated, allowing the operating system to manage process scheduling. Third is the central processing unit, or CPU registers. These are the values stored in the CPU's registers when the process was last running, including the program counter, stack pointer, and general-purpose registers. Fourth is the memory management. This includes information about the memory allocated to the process, such as base and limit registers, page tables, and segment tables, enabling the operating system to manage memory allocation and protection. Here are some additional components of process control block. First is the input or output status information. It tracks all input or output devices allocated to the process and open files, ensuring proper input or output operations. This includes list of open files and their status, input or output device allocation information, and input or output request queue pointers. Next is the accounting information. It stores usage statistics for billing and performance analysis, allowing the operating system to monitor and optimize resource utilization. Example of the process control block accounting fields are the creation time, central processing unit time used, time limit, and the priority. Let's discuss the structure and implementation of a process control block, focusing on how it can be defined in the C programming language. Here is the C structure for PCB. We start with the process identification, including the process ID and parent process ID. Next, we have the process state, which can be ready, running, waiting, or terminated. Then we have the central processing unit registers, including the program counter and an array of registers. Finally, we have the memory management information, including the memory base and memory limit. This is a simplified representation, but it captures the essential components of a PCB in C. Now let's see how the process control block plays a critical role in context switching. Context switching is the process of saving the state of one process and restoring the state of another, allowing the central processing unit or CPU to switch between processes. Here's how it works. Step 1 is to save the current process state to the PCB. When a context switch occurs, the operating system saves the current state of the running process into its PCB. This includes the values of the CPU registers, program counter, and other relevant information. Step 2 is to load the next process state from the PCB. The operating system then loads the state of the next process from its PCB, restoring the CPU registers, program counter, and other information to the values they had when the process was last running. Let's summarize what we've learned about the process control block. The process control block is a data structure that contains all the information needed to manage a process in an operating system. It enables context switching by storing and restoring process state information, allowing the CPU to switch between processes seamlessly. It contains process identification, state, central processing unit registers, memory management, input or output status, and accounting information, providing a comprehensive view of each process. PCB is created when a process is created and deleted when the process terminates, ensuring proper resource management. It is stored in protected memory space accessible only to the operating system kernel, preventing unauthorized access and ensuring system stability. Thank you for watching. Hope you liked the video. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.